Thank you everyone for coming, and I'm very happy to be here as a new member of the group. And today I will give an introduction to the so-called little Roost-Papa theory. Or the argument would be anti-concentration. Phenomenons. So this has been the focus of my research for more than a year now. Now, many proofs in probabilities rely on bounding the probability of rare events. And the most frequently used tool in such argument are concentration inequality. So a typical concentration inequalities tells us that if we have if x is a nice random variable, for example, sum of independent random variables, then x is concentrated around its means, or in other words, the probability that x minus the expectation to mean of x, let's say smaller than t, where t is the last number is small, is big. So for example, Chernoff inequality is one of the most famous examples. So anti-concentration is a phenomenon in the opposite directions. So it says that again x is a nice random variable.
That's different nice.
Right. Yeah, it's something. Then x is say locally well expressed. But it says that, so there is a red line, and we have some small interval anywhere in the real line. Then this says the probability that x is in I is small for every small interval. So this type of inequalities also have many applications, especially in the random matrix theory. And to illustrate these two phenomena, I will use the central limit theorem. So the central limit term says that if we have Sn id random variables independent and identically distributed random variable, and let x denote to be the normalized sum of the xi. Okay, so maybe one more condition. The means of the xi is, for convenience, let's say the mean of xi is 0 and the variance is 1. Then the central limit theorem says that if we denote by x the normalized sum of the xi, then we get a random variable which is approximately normal distributed. So it converges in distribution to the normal distribution with mean 0 and variance 1. I was wondering whether there are in there are 3 was because I see unexpected. So in other words, the probability that x is at least t is let's say approximately 1/2 pi. So this is the right hand side is a probability that the normal random variable is bigger than t. So it's 1/the square root of 2 pi, the integral from t to infinity of is minus x squared over 2. So if t is sufficiently large, then this is of order e to the minus t squared over 2. Maybe we multiply with some smaller order term. So in particular, when t is small, when t is big, then we get a concentration inequality. This form. So if in the if in the central limit theorem, we assume further that the test moment of the xi is also finite. So with the condition that the test moment of the xi is finite. Then we also know the rest of conversions in the central limit theorem. So we have a quantitative form of the central limit theorem. So it says that probability that x is at least t minus the probability that the normal distribution is at least t. This is a small 1 over square root of n. So the test moment is hidden in this notation. So by using this, we can see that the probability that x is discrete. Thank you. So here we take any interval containing V, then the probability that x equal V is of course smaller than the probability that x falls into the interval containing V, right? And this is well approximated by the probability that the normal distribution is into the interval I plus this noise. So if we have this is normal distributed, there is a probability that Z is yeah, I'm a little bit informal here.
Are you assuming that the x is discrete random variable?
Yeah, for this talk, x is a discrete random variable. But this is true for, I think, for general random variables.
Because otherwise I was afraid of what it means.
Yeah, if x is continuous, then this probability is 0. So here I focus on the discrete random variable. And if you for continuous, then we have to like V by the small interval. And actually this is because this probability is 0 if I is small. Then this is about osmos 1 over root n. And actually this bound is sharp. For example, if you choose n to be an even number, so the parity of n is not important. For simplicity, let's say n is even, and the hi is the SID random size. So that is the probability that xi is minus is 1 equals the probability that xi is minus 1 equal to the half. Yeah. Then you can see that the probability that x is 0, x is the sum of the xi normalized by square root. Then that's the number of ways to choose n over 2 elements from a set of n elements, and you divide it by 2 to the n. And by Stirling formula, for example, we know that the right hand side is roughly 1 over root n. Yeah, if you have any question, please stop me. In the second line, this for is how for any t. Yeah. So the theorem says that is true for any t. So we have a uniform bar.
So the constant in the bigger location
Depends on the test moment. So I think it's 1.5 times the test moment, something. And actually, the first anti-concentration inequality was proved by Littlewood and Offhoff. So to this end, we can consider a linear form. I want x1 plus on plus in xn. And against the xi is the SID random size. And the condition here is that the all of the AI are non-zero for every AI. Then the probability that else equal V for a particular V is on the square root n. So if the AIs are comparable, then this follow from the variations inequality. Here because we have actually we have variations on central limit theorem for this. So square. So this is so this theorem. So Littlewood. In the 40s and Anders in 43. So Littlewood's offers prove a slightly weaker bound. They have a log n or square root of n, and then Anders improve it into the optimal bound. And he even get this bound n choose n half divided by 2 to the n. And his proof is very beautiful, and it's straight from the book. So maybe I can spend 1 or 2 minutes to explain the proof.
What is the variation? What is the variation theorem from? Do you remember? What year is variation from? That year.
That theorem, variations. Variations is this theorem.
When? Like 19 something?
In the 40s. It's not older than not older than this one, or not much older. So the proof goes as follows. For every instance of the random variable xi, such that the linear form, so functions of the x equals v. We can associate this with a set I. So I is a subset of the set from 1 up to n. And how do we define I? So I record the indices I such that xi is 1. Maybe before this we need two small reductions. Is that we can assume that the AI is the absolute value of AI is at least 1, because we can divide it by a small number. Then we get this condition automatically. And moreover, because the xi is symmetric around 0, we can flip AI. So we can assume that AI is. So we can. So the AI is bigger than 1 for every I. Yeah. So we can do this simple in reductions. And the claim is that the family or the collections of of the set A from an anti-chain is anti-chain. So that there are not two sets A and B in the family, so that A is contained in B. So that does not exist A, B in the family F, such that A is a subset of B. So that's the definition of the anti-chain. Yeah, maybe. So it is not difficult to see that this is must be an anti-chain, because, for example, if we have a set, let me prove it by picture. And let's say this is our A and this our B. And this set is B. A is a subset of B. Then the value of L as this instant is strictly smaller than the value of L as this instant. So let me call this collection, if it's a name F. So because F is an anti-chain, so by Spanner theorem, we know that the probability that L equal V is at most, or is exactly the cardinality of F divided by 2 to the n. And by the Spanner theorem, you know, because F is an anti-chain, the cardinality of F is at most n choose n half. So this probability is at most n choose n half divided by 2 to the n. And you see that this bound is optimal. And this fundamental inequality has a lot of applications in different areas. And it's from its inception, it enjoys many extensions. So for example, we can consider general SI, not necessarily random size. And we have the so-called inverser Littlewood theorem. So this by so in around 2006 and between 2006 and 2011. So I think it was first proved by Tran and Wu. So they proved this inverse Littlewood offer theorem and then apply it to some to a random matrix theory. And then the optimal form of the theorem was obtained by Van Vũ and Hội Nguyễn in 2011. So this, I will not state this theorem precisely. So it roughly says that if the probability is a pi probability, so the probability is that a1 x1 plus so on plus an xn is large. So here, for simplicity, I will only consider the random sign. Only the same. It says that if this probability is large, polynomial C is large, then the coefficients set A1 up to AN is well structured. So in a sense, this theorem is expected because if this probability, also the probability that is equal particular number is large, then a lot of this sum agrees must be the same, and if a lot of these are the same, then somehow the AI has to be very well structured. For example, so this set has to be contained in a small ZIP, generalized IP.
So the particular vector V is something even and fixed.
So this is true for every V. So if there exists a V so that this probability is big, then this set is well structured. And this term has many important consequences especially in random matrix theory. Right. Something like 30 minutes. So here the proof is like crucially on the fact that the xi's are independent. But in many applications we want to prove such inequality for dependent random variables. So we have against A1, AN real number. And we have a linear form. Now we have A1 eta 1 plus AN times eta n. And here's the eta n is drawn uniformly as random. From the set, from the Boolean hyperq, subject to the condition that the sum of the AI of the eta I is exactly n over 2. So here I ignore the parity of n because it's not important here. It can be any number which is linear on n. So of course this random, so the eta I is not independent, right? Because here we have the constraint that the sum of the eta I is n over 2. So the eta I are not independent. But in many applications, we still need to, or we want to prove an anti-concentration for this linear form. So for convenience, I just denote P of I. I stand for the coefficients II. Is a supermove of the concentrations of the point probability. So somehow intuitively, if this number is big, then somehow the coefficients II also must be very well structured for the same region. So maybe I will state an analog of the Littlegoose-Orford adder theorem. So that's this. So I assume that there exists a set of indices Z. So Z is a subset of the set of number from 1 up to n, and the cardinality of Z is K. And with the property that Vi is different from Vz for every I is not in Z, but Z is in Z. So we have two sets. So here we have Z, and here. So for I and Z complement. So Vi from this set is different from Vz from this set.
So what is Vi? Okay. Do you have a given numbers?
Yeah, sorry, I mixed it up. So this that's coefficients. That's the I from here, AI from here. For example, if we have the first half on the AI at 0, and in the second half on the AI is 1, for example, then you can take that to be this set of indices from 1 to n half. So under these conditions, under these assumptions, then the probability, the point probability is as most of order 1 over square root of K. So this type of inequality is useful when you study random matrices with dependent entries. But of course, we want to go beyond the 1 over square root of k bar. In many model of random matrix, we want to get a bound which is exponentially small. So this is not strong enough for that purpose. So this one already has some nice application. Mm-hmm. So then this will be, I think this will be the this is the minimum between k and n minus k. So k is not n half. So does this answer the question? Then you get 1 over square root of n of order 1 over square root. So it's similar to the adders, to the least good offered adders. But here, of course, you need this type of condition, right? Because if you have all the AI are the same, then of course L is always a constant. So this point probability is 1. So somehow the anti-concentration inequality in this setting has to capture or has to root out this situation.
But if all AIs are distinct, then you can take a K1.
But we want to test K as big. K such as K and n minus K minimum is as big as. Right. Because we want this to the right hand side to be as small as possible. Yeah, I think this condition is kind of natural because it root out this situation. Because when all of the AI are the same, then.
Do you assume that AIs are positive?
So if the AI.
We need to assume that AIs are positive because otherwise I can flip some signs and then make like say as I want. Oh, I see. So beta is okay. Never mind.
So anyway, this bound will never give a better bound than 1 over square root n. And in many situations, we want to have a exponentially small bound. And also in some situations, we want to prove the anti-concentration inequality for polynomials of the dependent random variables. Because actually many natural combinatorial statistics can be interpreted as a polynomial of the random variable eta I. If we draw some vertices of psi n half from the graph, then, for example, the number of triangle and many other statistics are polynomial of this random vector. but maybe let's stick to the linear form. Somehow polynomial is more difficult to deal with. So again, this is also that the difference is between AI and AI should place around in the anti-concentration inequality. And actually, I think my main contribution to this theory is a result of that type. So I prove something like if the point probabilities pi is large, then the differences are smaller than this. Is graph structures. Yeah, maybe I will not go into the statements of but I will test on corollaries. For example, from this type of result, we can prove the following. Let's consider this model of random matrices. So the Qn is a random n by n matrices. So here we have Qn. And the this is 0, 1 matrix. So the Ii is either 0 or 1. And so the constraint here is the rows are independent, and the sum of the entries in each row is exactly n half. So you take the sum of the entries in each row, you get n half.
When you say independent, they are independent as a vector space, not as a random variable.
As a random vector.
It's a linear.
As random vector.
As a vector, they are linear independent, or
no. What I mean is that
as a random vector, they are.
So we draw Qn uniformly as random from this space. Then you can see that the rows are independent.
Okay.
Because between any two rows there is no relation. And of course, one of the most fundamental questions in the random matrices theory is to to estimate the probability that the random matrix is singular. So in this case, we are interested in the probability that Qn is singular, or the Qn's, or the rows of Qn are linearly dependent. So we prove that this exponentially small. Let's say put 2 here, so that is true for every n. C is a constant bigger than 0. Let's say, for example, we can take C to be some small number like this. So, any questions so far about this model of random matrices? So maybe I will give you a little bit history about this problem. So I think this model of random matrices were introduced by Nguyen. One, yeah, we introduced it by this guy. And he proves that this probability decays faster than any polynomial. So I think in 2013 he proved that. So this is just a brief history. The probability. So maybe for convenience, I denote this one by Qn. So for every c bigger than 0, we have Qn is as most n to the minus c, but n is big. So it decays faster than any polynomial. And his proof is the inverse little goose offer. So then more recently, Asaf Faber, Zen order, alphabetical order. Faber, Zen, Kaitlus, and Voitek Samuti. They prove that Qn is something let's put this C here for some small constant C. So our result says that C should be 1. So they, okay, let's put it this way. And after the multiplicative factor C in the exponent, this bound is optimal. For example, if you want to look for a lower bound, and you can see that this is at least the probability that the first 2 rows are the same. Of course, if the first 2 rows are the same, then the matrix is singular. by a simple counting argument, you can see that this is something so simple. So 2 over n choose n half. Maybe 1. Because if we fix the first row, then there is a unique choice for the second row. And we draw it from the set of sign n choose n half. So the probability is on. Yeah. So it is not difficult to see this lower bound. So this roughly half to the n. And we can conjecture that this simple lower bound is tiny. So he said the right hand side should be a half to the n. Up to this little one, which tend to 0 when n tends to infinity. Or say for every epsilon bigger than 0, there is n naught, so that for every n bigger than n naught, then the probability that Qn is singular is smaller than 1/2 plus epsilon to the n. And so maybe let me mention one more application of that phenomenon. So there is another model of random matrices with dependent entries, which attract a lot of attention. Is the following one. So we have Qn, so maybe this one is Pn. Let's say Mn. So Mn is drawn uniformly as random from the following space. So here we require that the row sum is n half. But also the column sum is also n half. So this corresponds to the adjacency matrix of a regular digraph of degree n over 2. So there is a combinatorial interpretation of this one. Right, it is 0 on matrix. The constraint is that the row sum and the column sum are the same. This equal sum can be any constant time s. So n half here is not important. I think range. So up to a permutations. These two left. So they consider this model and use a tool which I have developed to prove that, to prove exponentially small upper bound on the singularity probability. This other thing. Actually, I posted my paper to archive on middle of July, and this guy proved this result on the middle of August, so that's 1 month after my paper.
So they use your theorem to prove this.
And with, of course, they have some clever twist, additional twist to the tool which I developed. So let's explore into this. So in a little bit of the joint work with Matthew Kwan and Benny Sudakov, we proved anti-concentrations inequality for polynomial of this vector, random vector. But of course, we only get something like 1 over square root of n.
Is there any bounds on the degree of the polynomial?
It's constant. Yeah, we can allow the degree to go slowly to infinity. Maybe log and log. Yeah, I think. Do you have any other questions?
Maybe let's take the speaker first. Yeah, maybe can you write your collaborators' names just in case they might watch your video?
We prove an anti-concentrations. Polynomial, let's say. Let's put for quadratics. Of the vector eta I. So the proof of this theorem is a decoupling argument, and that argument is actually come from the proof of these propositions. So then we apply that decoupling argument to transform our quadratic form to another quadratic form, but now the coefficients are random. So
could you tell us how to obtain this Roller phenomenon? Are there many technical steps in there?
yeah, there are many technical stuff. We are also little develop new stuff. So if I zoom this, I zoom the anti-concentration inequality, then the proof of that to deduce the curly is maybe takes for 15 pages. So it's not a direct sequence.
What is not clear to me is that we have this random matrix with n random vectors. But you somehow need to kind of get back to the linear.
Right. Okay. Maybe. Okay. Maybe I can explain the connection between this random matrix model and with that phenomenon. I think that's the question. So the Qn is singular. So maybe first so Qn is an n by n matrix. For convenience, I denote each rows by R1, R2, and so on. I use capital. And the Ri here is draw from copies, independent copies of the eta. Eta. And Qn is singular. If only if there exists a non-zero vector or actually for convenience we can say is a unique vector by normalizing. So thus Qn times V is a zero vector. So this is equivalent to the following conditions. So V, right, because the multiplication between a matrix and a column vector is that consists of the inner products. So I split this into two parts. So I will condition on the first n minus 1 rows. So this means that V is so V is orthogonal to the span. And V is orthogonal to the Rn. Nothing happened here. So here, and I assume that the, let's say for convenience, the Euclidean length of the vector V is 1. And of course, if we conditions on the Ri, then V is uniquely determinate. Because here, if we have n minus 1 independent vector, then the orthogonal complements of the space is one-dimensional. So V is uniquely determinate up to the sign. And if we can prove that for typical choices of the first n minus 1 rows, V is kind of unstructured. Then here we need to bound the probability that I and V is 0, right? And V is so by conditioning on the first n minus 1 rows. If we can prove that V is unstructured in that sense, with for typical choices of the first n minus 1 columns rows, then we are done. So I think that's the connection between the two.
Any other questions?
And of course, so I think a huge chunks of the pages are devoted to prove this. This lemma. This.
Any further question? Maybe we can continue with the dinner place. Right? Okay. Let's thank the speaker.